I will go through a very short deck of slides, about 10 slides, talking a little bit about some background. And then we will go into the neuromatch materials for base day, which I think is really useful because you get to do the computation instead of just me being like, here's a slide of what the output of it is. So I think that's particularly useful. And please ask me questions whenever those questions come. And I'm still having my coffee here in here in America. It's 6:30 on the East Coast at the moment. So I did need that coffee. So today we'll be talking about Bayesian modeling of behavior, not primarily about the research, but about the techniques that we use for that. And let's jump right in. So Bayesian models are an example of so-called normative models. What's a normative model? In a normative model, we say there exists something that the system is trying to achieve. Maybe I want to move my hand with minimal variance. So I want that my hand is as close to the target as possible. That's what we call an objective. You can say it's a cost, the economists call it the utility. There's many different ways of calling it, but the idea is that there is something that should be optimized. And that could be, say, the energy that you use while you walk. That could be you want to minimize the errors while you move. That could be, if you play the game of darts, maximize the amount of score that you get. There's a lot of aspects of it. And then there's bounds, there's constraints. Now, let's say my visual system doesn't allow me to localize something more precise than, say, the precision with which I can know into which direction my eye is looking. Or if you close your eyes and you hear a sound, you will be even worse. And you can say it's about 30 degrees that you know where the sound's coming from. And now, how do normative models work in practice? They try to calculate the best possible solution that we could have. Maybe I go and say, I have a simulation of walking, and how can I tune all the parameters of walking so that my walking minimizes the energy that I need to burn to get from one position to the other. And then once we solve for that position, we compare that then with the actual behavior. When we talk about Bayesian models, usually the constraints are in terms of noise that we can't get rid of, and actual behavior is behavior in a situation where noise somehow makes sense. The first thing that I wanted to say here as well is, for people who get interested in Bayesian statistics, we just finished writing a textbook. It's a textbook with Vijaykumar and Dan Goldreich. Its title is Bayesian Models of Perception and Action, an Introduction. And it's free and it's online. And we're still looking for feedback because it will be printed by MIT Press starting from October. And you can download it and make comments at Bayesianmodeling.com. I'll be happy to give you the links for that later, but it's just Bayesianmodeling.com. And everything that I teach today will be a tiny, tiny, tiny subset of this book on Bayesian modeling. Now, what are some questions that we ask, that we really want to ask? And why do we want to use Bayesian statistics? One of the points is that we might want to make predictions. I want to predict what's the probability for future data that will happen, given maybe a model that I have and data that I have. That can specifically mean what's the probability that I will hit the target, given that I choose to go some direction and what I just saw. We can use similar ideas to choose models, where you can say, I have two models, model 1 and model 2. I calculate what's the probability of the data that I have given model 1. What's the probability that I have of the data given that I have another model. I prefer the model that's better at explaining the data. We can also use it to make decisions. We can say we have a utility function, u of x, given what I choose, there's going to be a distribution of the different x. I want to integrate out all of the x. So those are just three of the possible things for which we might want to use Bayesian statistics. Now, specifically for today's talk, much of it is about uncertainty in terms of movement or uncertainty in terms of me localizing something. I see things, but I'm not arbitrarily precise. I hear something, but I'm not arbitrarily precise. I want to make estimates with it. And I should mention there's a really long history worldwide, in fact. The oldest work probably goes back to al-Haytham or Ibn al-Haytham. That's work from the 11th century, who wrote the book on optics, and who already said that perception requires unnoticed judgments. So in a way, the idea is there's a world out there, I see things, and I'm making a model of how the world makes the data that I actually see. It's also nicely said a full 900 years later by Pierre-Simon Laplace. One may even say, strictly speaking, that almost all our knowledge is only probable. And in the small number of things that we're able to know with certainty, the principal means of arriving at the truth, induction and analogy, are based on probabilities. And finally, there's the work of Hermann von Helmholtz, who says that we should think of perception as unconscious inference, where inference means that we basically solve this probabilistic problem of the world makes something that I have, what can I in turn say about the world outside? And there's fundamental assumptions, of course, that we make in a way, like most Bayesian models make philosophical assumptions like this. So we can say there is something outside. It makes the data that we observe, and we have some kind of an assumption, and then we are concerned with the probability of the data given the model. And within Bayesian statistics, we often use so-called Bayesian models to denote that, where we can say we have a stimulus in the world, let's say X. That stimulus X affects the things that we see and hear. A would stand for audition, what we hear. V stands for vision, what we see. And the thing outside in the world, that model that Hermann von Helmholtz was talking about, is what gives rise to what we hear and what we see. Now, in practice, we want to do the inverse of that. We have what we hear and see, that's what we know. And we are effectively asking the question of what does that mean about what's outside in the world. And when we do experiments, of course, that X here, that model lives in the computer that we put in front of the subjects. Now, here we have Bayes rule, which is the tool that we often use for it. We want to know what's the probability of A given B. What's the probability of, say, there being a certain location given what we saw? Well, that's the probability of there being that location, the prior location, times the probability of B given A divided by the probability of B. And you can derive that rule from the so-called product rule, like the probability of A and B is the probability of A times the probability of B given A, but it's also the probability of B times the probability of A given B. You equate those two, you can prove Bayesian. Now, enough about the introduction. It's time to jump right in. What we will want to do today, and it's an experiment, I've never done that with the group before, but I think it will be really useful, is that we will now take those materials and in Python actually solve a couple of Bayesian tasks and go along with a tutorial that teaches Bayesian methods And I heard that a lot of you already went through the Python bootcamp. What I encourage you to do is, in a way, to link up with one another, and ideally we'll see how we best do that on the tech side, but so that you can also help one another. I will be there with you all the time, and in any case, it's an experiment. Let's hope that it works well. So, Neuromatch Academy. For people who haven't been to Neuromatch Academy, this is a 3-week summer course. We hired hundreds of teaching assistants. We normally have 1 teaching assistant and 10 students in one group. They stay in that same group for 3 weeks. Every day, they do 4 hours of learning, for example, about Bayesian statistics, with the kinds of materials that you will see, and then they spend the afternoon working on projects. So in the end, it's a very intensive 3 weeks course where people learn about computational neuroscience and develop their skill levels. So let's, let me end the slides here and let's jump into Neuromatch Academy. And I will need to make sure that you all have the right link. So let me quickly distribute that link here. Course materials here. So these are, just to be clear, these are last year's materials. So here we have Neuromatch 2020. It's last year's materials. So what I want you all to do, and hold on, let me also go to Bayesian modeling.com. It's early morning for me. I might be bad at teaching you Bayesian things, but if you're interested in that, you can just go and read our book for free, and it should have a lot of that useful information. So I want you all, to everyone here, by themselves, to go to this Neuromatch webpage. I pasted it into the chat. And what we will do is you will now go there and you will scroll down to week 2, day 1, Bayesian statistics. And there it says tutorial 1, tutorial 2, tutorial 3, tutorial 4. Today, we will just do tutorials 1 and 2, because this is material that takes 4 hours taken together, and we will not have enough time. And of course, I'll be happy to post the slides as well later. Although arguably, the intro slides that you can find here are better than the ones that I had. So please, everyone, open this. And I want to first here emphasize a few more things. So what you see here is the so-called Google Colab. Google Colab is a hosted version of Python notebooks. What is that? It basically means that this is Python, but not running on your computer, but running on Google hardware. Does this and to get started, so let's first make sure that that this works for you. The first thing is, what we'll do is I want all of you to click on video 1 here. It will usually take a little bit because Google needs to give some compute for that. And here it is. Has everyone succeeded at getting the video running? So hold on, let me also say a little more about how this came about. A very large number of volunteers, in the end, hundreds of volunteers, came together to try and make these materials really well. So this is not a material made by one professor. This is material made by a very large number of people. And I should say here, the day's materials were done by Vincent and Matt with a little help from me. And then Matt, Jesse, Carolina, Said, and Michael all made the materials better. And a lot of additional unnamed people also helped with it. So what's the tutorial about? It's the first set out of multiple tutorials. We will talk about how we combine with prior information, where say sounds originate from, with sensory information, the so-called likelihood that sounds come from a particular location. The idea here at first will be that vision sets up a prior and that we want to localize something, but we can also use what we see to estimate it. Now, what will we learn in this specific notebook? We will learn how to implement a Gaussian distribution in Python. We will use Bayes' theorem to find the posterior from a Gaussian distributed prior likelihood. We will change the likelihood mean invariance and see what changes. And maybe in the next set of slides, we'll talk about what happens if you have the mixture of two Gaussians. Now, now let's talk a little bit about how we will do that. So each of you will listen to the videos by yourself. And then after the videos, do the exercise yourself while I'm basically here to help you. And for that, it's essential that you will need to tell me where you get stuck. But before we do any of that, I want all of you to turn off the sound, because you will need to then, take that first video and watch it yourself. And I will do the same thing so that I know all the bad things that I said. So why don't you all do that? And here we go.
Well, much of my research in the past has been about popularizing Bayesian approaches. And now I've been working a lot of machine learning in neuroscience. And this idea of Bayes-like models in neuroscience has always been close to my heart. So that's why I'm very delighted to be with Bayesian statistics. Another little fact about me is I'm also a big-time salsa dancer. Together with my wife, we in fact choreographed the University of Chicago here for a long time. Another fun fact is we use Bayes data for experimenting with the format for neuromagic. In that sense, let's jump right in. Let me give a little bit of context. Bayesian models.
So there's one more thing that I wanted to say. Now, like in Google Colab, if you want to run something, you need to click on these little start things. Otherwise, it just doesn't run. Or just make sure that you start it like that.
Why models? We often build them to understand behavior. And in fact, in this second week, you will hear a lot about modeling. We need to have ways of thinking well about behavior if we're to understand models. And uncertainty is everywhere. So therefore, dealing with uncertainty, dealing with statistics is really central. Just about anything that we do. It is a day dedicated to statistics. So we will have to give some background, think a little about the relevant mathematical concepts. Now, let's jump right in. Part one, Gaussians, their multiplications, and what that teaches us about Q combination. A simple example of Q combination is visual auditory Q combination. As you see this video, you see me in the corner. The sound is coming out of your loudspeakers, and yet you will have a very strong illusion that makes you hear the sound come out of my mouth. But that's of course not true, it comes out of your loudspeakers. So for illusions like that, we often study them in the laboratory. What we do is we give a visual stimulus, and at the same time, we give an auditory stimulus. Now what we can do is we can move the location of the auditory stimulus relative to the visual stimulus. And we can ask our subjects, tell us where you heard the sound to be. Here, there. Move the stimulus through the whole area to ask the question of how people solve this concept. So how should we model such a situation? We can say that vision gives us some prior information. What do I mean? What I mean is, if we look at the screen and something flashes there, we will be able to know exactly what it is. Our visual system is very, very good. At least we will be very good. But what does that tell us that we see? Well, what we might believe that it tells us is that it's much more likely that some sound will come from the vicinity of where we just saw this visual stimulus pop off than from a different location. And so we can, in that sense, say that vision sets us up with a prior belief. We'll say that it is more likely that the auditory stimulus that comes afterwards will be the vicinity of this area, less likely that it is further away. So we might believe that the right equation to model this prior belief of ours is a Gaussian. So let's go through the component of the Gaussian. The Gaussian is a probability distribution, which means it adds up to 1. It is characterized by mean and standard. Is e to the minus x minus mu squared divided by 2 sigma squared. Now, as we move mu, the maximum will move. Sigma will characterize how wide that is. Now, that's the equation for the Gaussian. Why do we need to learn about it? So, due to the central limit theory, many real-world distributions are in first approximation. So many, in fact, that large branches of statistics are dealing with Gaussian cases. And much of what you learn in Introduction to Statistics is about Gaussians. Also, me coming from Germany, it was on the German 10 mark. And that alone is a reason that we should think about Gaussians. So now it's time for you to implement a Gaussian in Python. Here you can see the equation for the Gaussian and write a function that sets up the my Gaussian function. Enjoy.
Okay, great. So I just finished listening to the video. My listening to me for this tutorial isn't essential, but you can always do that. But I will basically comment a little on as I go through it. So what we do here is we first do some more setup. Now, please execute the cells below to initialize the notebook environment. Why do we need to do that? In Python, we will use packages like NumPy and matplotlib, and we need them. So we'll run this. Therefore, now we have NumPy loaded. We use figure settings. This is just so that we can meaningfully see things. And we need a few helper functions. So as the video said, we should implement Gaussians. So the central thing there is the Gaussian equation. Like the Gaussian has its parameters mu and sigma squared, and it contains 2 parts. It contains this first part, which normalizes it. This makes sure that the sum of all the possible probabilities in the Gaussian sum up to 1. And then it has this part here, e to the minus x minus mu squared over 2 sigma squared. If we do it like this, it automatically does it. But like there's 2 ways how we could implement this in Python. Now we can implement this and then just add up and then just divide it by the integral of this. So alternatively, we can implement that. So now that we're here, it's time to implement a Gaussian. So what we want to write is write this function, my Gaussian x points mu sigma. So x points is where we want to evaluate it. Mu is what the mean, and sigma is the standard deviation. So what we will need to return is px, which is the probabilities here. And as you already had Python bootcamp, why don't you go ahead and already implement that? I just want to remind you that, say, if you want to use something like the exponential function, you need to get it out of NumPy. So we have np.exp. Also, if you want the power function, like z star star 2 means z squared. Z star star 3 would mean z to the power of 3. And there's also, we have raise not implemented error. This is what happens if we just run this. I should also say at neuromatch materials, what you usually see is what the results should look like in XKCD style. So we do that so that you know what you're driving towards. There's also always a solution, but don't use the solution, don't cheat. You can solve this time here. So I hope you're all already working on it. Maybe a little hints of what we will definitely need to do as we implement what px is. We need to comment this out because we no longer want to raise an error, and we will want to uncomment that. So we want to call px, and we want to do the plot. We should. This is hilarious. Okay, great. So there will be people that run at different speeds in this community, and so I don't want to overly push you to do it faster. In particular, my experience always when teaching these things is that people don't like kind of saying, oh, wait, I'm not there yet. So I will purposefully go slow on that. But let me try if I solve it, because it's been a long time since I last did it. So the Gaussian is, we needed to, so let's zoom here. We see we need an exponential of x minus mu squared. So let's do that. We need exp, but the exponential function. But exp isn't going to work because exp is part of numpy. So we need np.exp. And then inside of it, we have x minus mu over 2 sigma squared. So we will definitely need 1 over 2 times. It's 1/2. And now we need x minus over 2 sigma squared. Let's see here. 1 over 2 times sigma squared. So pressure's on. And then we have times, and then we have a mu minus x points, x underscore points squared over 2 sigma squared. Is that it? Maybe that's it. But now without it, this is not going to be normalized. Now we need to normalize it. So we can say px is px dot px divided by px dot sum. Yes, presume. Let's see. Running. Oh, that doesn't look good. That doesn't look right. Oh, yeah, look here. Why is it not working? Because it's negative and I made it positive. I forgot the minus. Let's run this again. Oh, look, there's my green Gaussian. That looks about right. Cool. Okay, cool. Now we have here an implementation of the Gaussian. And let me already, I always like playing with things in such scenarios. So, so here we had a Gaussian with a mean of -1. What happens if I make it, instead of a mean of -1, make it 1? Let's just see. Oh, did you see it just moved from -1 to -1 as it should? Great. So let me just make sure. Has everyone in the audience succeeded at making the Gaussian here? If not, let me know right now. Last chance. Okay, looks like everyone's there. Now, why don't we then go to the next video on Bayes' theorem? So let's watch this.
So now that we have the Gaussian, let's see how we can build a Bayesian Y model with that. We assume that vision is near perfect and sets up a prior belief where an auditory stimulus may occur. We assume that there's a constraint, namely that audition is noisy with irreducible uncertainty about the direction where we had something to become. And then we assume that the brain has the objective of minimizing estimation errors. What do we want to describe? Well, we want to describe the way people estimate auditory locations when uncertainty is involved. So let's think about what arrives at the brain. There exists a true stimulus at some place, but this true stimulus isn't directly accessible. Instead, in some trials, we might hear it to be a little further to the left, and others, we might hear it a little further to the right. So in other words, if the true stimulus is always the same, the brain encoded stimulus will vary from trial to trial. So what does that mean? The true stimulus might be here. The brain encoded stimulus on a given trial might be further to the left. What does this mean? It means that the encoding that we have in the brain is most compatible with the assumption that the true stimulus is actually here. It's less compatible with it being left or right. If you would not give me any prior information, I would think it's most likely that the stimulus is here and less likely as we go away from this. Now, Bayes' rule that you heard about in the introduction allows us to do such calculations. What we want to calculate here is what's the probability that the true stimulus is at a hypothesized location given the encoded stimulus that we have. So we want to calculate this, and it's called the posterior. Now, how can we calculate that? Well, we need to take the prior, which is the probability of the true stimulus, the probability that the hypothesized stimulus is the true one that we know based on the distribution in that context of like seeing this visual stimulus here, times the likelihood function, the probability that the encoded stimulus in the brain has the value that it has, under the hypothesis that the true stimulus has a certain value. And now, like all probability distribution, this must add up to 1. Therefore, it is divided by the probability of the encoded stimulus, which is the so-called partition function. So, to do so, it contains the product of two terms, the prior probability and the likelihood. And for the example that we're currently working with, both of them should have the form of Gaussians. So now let's see how we can multiply such Gaussian. It's time for you to implement that. You will be calculating the posterior for which you will multiply the two of them, which tells you how, based on the prior knowledge and the auditory knowledge, how probable it is that the true stimulus is at each possible hypothesized location.
Okay, great. I presume you guys, some of you might be able to hear me. Others of you will be quickly typing already. So let's talk. So what we will be doing is we will now basically implement that multiplication of the two Gaussians. Oh, here, Abi raised the hand. Please go ahead. I don't know, host, if we need to.
1 second. I will.
Yes, I can hear you. Great.
No, I have to unmute her or the. 1 second. Has she been unmuted? Yes.
Thank you for asking a question. What's your question?
Oh, okay. She doesn't have a question.
Okay, great. Then why doesn't everyone continue? But also I want to encourage you, like I'm here so that I can be helpful. So please feel free to ask questions. So while we do this, I will also be solving this here, the posterior. As we said, the posterior is the prior times the likelihood. But prior times likelihood needs to be normalized. And like that's where we have P of A times P of B given A divided by P of B, because it needs to add up to 1. So we need to have posterior is posterior divided by posterior dot sum. Okay, now we should have the posterior. Good. And that should calculate that. Now we need to still calculate that here. Let me first remove that not implemented error, because we will be doing that now. This is my Gaussian. Good that we implemented my Gaussian earlier. At the points x, comma, we need a mu auditory, comma, sigma auditory.
There's a typo there, Konrad.
Yeah, where's my typo?
Instead of auditory, it says audiotory. Mu.
Oh, cool. Great. Mu auditory, sigma auditory. And then we have visual is equally my Gaussian x, comma, mu.
There's also a question in the chat box. Fernando is
wonderful.
asking, are we summing or integrating? I mean, Gaussian is a continuous distribution, right? Is the question.
Yes. So this is a great question. In practice, when we do simulations, what we usually want is that if we add across all the bins that we have, the probabilities, we want to add up to 1. Now, in principle, we could use bins of 1, in which case that problem goes away, or we can alternatively carry this delta with us. In practice, it's continuous, but in our simulation, it's discrete. We just have enough points so that it effectively gets to be continuous. But it's a great question. Now let's see here. X mu visual, comma, sigma. So, okay. Now posterior is compute posterior pointwise. I'm not sure if it needs normalization or if it's already normalized. So let's see if this runs. Run Excel. Okay, let me see. Oh, what's happening? Nothing's happening. I clicked on it. Okay, it's running very quickly. It's not, oh, I need to uncomment this, of course. Here and here. Ah, look, there's a mistake. Oh, there's an indentation error. Where's my indentation error? This should be one further to the right. And it's still not working. What's happening? Does anyone see how I'm wrong here? I must be making a mistake here. Oh, that is. I should delete the last two lines. No, there's somewhere it's not. Somewhere the plotting is not being called here. Yeah, no, we will need those lines because otherwise it will not actually call anything. Comment the raised. Oh, look, here it's raising an error. Thank you. In fact, I think this is also one of the things that are very important and why I like this mode. It's important for everyone in the audience to see that even people like me who've done a good amount of these things, we make errors and then we ask our friends and then they're like, oh, you actually just need to comment out the error. That's it. And so I think that that's very important. So here what you see is the results of that. We have an auditory Gaussian here. We have a visual Gaussian here. We multiply those two of them. It's this one. And what you see, it's more narrow. Why is it more narrow? No, like we use what we see and what we hear. Both of them help us know something about it. By combining the two of them will be better than only having one of them. So that's great. That's what we should expect. Now we get to an interactive demo. So what we did before, we used Bayesian and we numerically did it. Now, like what we did here is we said, okay, let's implement the Gaussian, let's implement the other Gaussian, let's multiply the two of them. But what we can also do is we can now see how that depends on things. So what we see here is we have these little wedges, and this is just so much fun. I can now change what the mean of the auditory stimulus is. Look at that here. Let's move the auditory one all the way to the right. Oh, look, the standard deviation doesn't change if I change that. No, so these sliders, I think it's really helpful to get an intuition for that. The green curve always seems to be square root of 2 roughly higher than the other curves, if they're the same. Now, we're in that situation. Now let's make the auditory stimulus be really crappy, because it turns out it's true. Audition is really bad. If you try to localize where a sound is coming from, somewhere over there, you'll be like plus minus 30 degrees. If I show you just like a little dot and you're seeing it, you will be precise to like well less than a degree. So let's make the auditory stimulus really crappy. Oh, look, in that case, basically, what we hear becomes irrelevant mostly for our estimate here. Now, audition starts having a really weak effect. It's mostly, so what we have here, this is what we call visual capture in the field. Vision is so good that audition is like almost totally ignored. So I want you to like really spend a few minutes playing with it. Just ask yourself if it makes sense. Now, like, what about the width of the green curve? What about the height of it? How are they related? And so on and so forth. So I want you to play another, like, just put yourself into the shoes of the experimentalists. What are the experiments that we could do? And how would the results look like? And for example, this is how it would look like if we do the experiment. In fact, people do these kinds of experiments. They just show an LED flash and then they have a loudspeaker. And even if that loudspeaker is quite far away, people say that they perceive the sound to be coming from the LED. In fact, that's happening right now. Now, like you probably have my video on your screen. Your loudspeakers are about 30 degrees angle ahead of you. And if you look at the screen, it probably totally looks like the sound is coming out of my face. I'm getting, okay, Sudeep, great question. I'm getting an error with the posterior plot. It is coming much lower than what it is supposed to do. Okay, great. So let's see. Do you want to share your screen? Let me stop sharing my screen. Can you, host, can you allow Sudipta to share their screen? Let's see what we can know, what we can learn from the error with the posterior plot.
Arun, are we able to do that?
Yeah, 1 second, ma'am. I will give the co-host option to Sudipta.
Sure.
And I mean, like, it's unlikely we'd be Zoom bombed, I think. I think everyone in this audience is trustworthy. Although, like, we organized a lot of NeoMatch conferences, and we had some real trouble with people who didn't like us.
Sudipta, you're now a host or a co-host. You should be able to share screen.
Oh, and I already have an idea of what it could be. I'm curious. Oh, yes, I think I know exactly what's going on there. Can you, let's look at, yes. So what you do here, Sudipta, is you multiply the auditory with the visual. But we don't just want to multiply them, we now also want to normalize them. So if you can go there, and after the line where it says posterior is compute posterior, yeah, but here you already compute posterior pointwise. Posterior is posterior divided by posterior dot sum. That looks correct. Huh. It is clearly, hold on, let's make sure, maybe there's a backup there. Let's try down here again, like where it says posterior. Let's add another normalization. I know only one of them should be necessary. I would add after line 33, just as part of debugging. Posterior is posterior over sum of posterior is posterior divided by posterior dot sum. Cool. Let's run that. Wow, and it still doesn't do it. Okay, so that's interesting. Posterior pointwise. Hold on, let's make sure it's hold on, no. I think I know what's going on. There's posterior and posterior pointwise. Yeah.
Hello. Oh, you can you hear me?
Yeah.
So here you have normalized using the sum function, right? So in the previous video, I mean in the previous code, I had put the the normalization constant as it was from the formula. Can it be the source of the error?
Possibly. So Arnab said they forgot to normalize the first code snippet. Let's see. Arnab, can you explain where the error is? Yeah, here it looks like, yeah, here you want to.
Hello.
Yeah, yeah.
Actually, I can't explain it by the theory how it is happening, but when I tried to do that, and I first initially made the statement where I was normalizing using that by dividing by that sum of the whole variable. When I kept that as a comment, and then I tried and then implemented both the codes, and then mine output is also coming in that similar manner.
Actually, can you go back down? I think I just realized what the problem is.
Yeah.
Because no, down to yes. So you're plotting posterior pointwise, but you're calculating no localization simulator. No, let's again, let's look at localization simulator, a simulation. Why is it not working? It looks like you wrote exactly what I wrote, but like it's
so let's just convert. I mean, this code. I mean, let me delete this part and divide it by px by some. I mean.
Yeah.
And px.
Oh yeah, that's possible. Px is px over some. No. Px is px divided by px.
Oh, sorry, I'm so sorry. Yeah. Oh, God.
And I want everyone to know, like, these kinds of errors, they like literally happen to everyone, and this debugging is how the life of the programmer. So yes. It's solved. That's it. It was calling the function from up there, which had like a yeah, awesome, cool, problem solved.
Oh, thanks. Also, like, why was it? I mean, I don't know why was it happening there. I mean, we use the sigma from the individual functions while doing this in the previous code, but why was it showing this issue?
The sigma of the individual functions? Hold on, no, I'm not sure I understand. No, it's calling the function that you defined earlier, because the function, we didn't override it.
Right, but like in case where in the given visual, so when I'm implementing my Gaussian x mu auditory sigma auditory, and when I'm implementing mu visual sigma visual, I mean, both the case should be same, right? If you do it in the some way, or you include the normalization within the my Gaussian function.
Yeah, no, it doesn't, and here's why. So keep in mind that when we do that simulation, we choose how many pieces we divide the axis by. Now, like we can say, have one point every distance of 1, or every distance of 0.1, or every distance of 0.001. For the normalization too, if you want to normalize the analytic way you did, you would then also need to add the 1 over how many divisions you have. Now, like if I have 10 divisions or 100 divisions, it will add up to 10 times as much.
Okay. Fine.
So you would need to, so technically there is a delta x that then goes into the equation. So if you add the delta x, it will again be fine, at least approximately fine. But if you normalize by adding, like by dividing by the sum, it automatically takes care of that delta x.
Right.
And I want to thank Vatsala here. You can now all ask questions whenever they appear directly, which I think is great and important.
So Rainier has a question. He has raised his hand.
Rainier.
Hello. I have a question regarding the widget. Then where you can just change the parameters. So I got a situation where the peak of the auditory is higher than the posterior peak. So
that is weird and impossible. So let's look at that. Can you share your screen this time?
Okay. I'm disabled to share. Okay. For example, here, so I'm getting a case where the auditory has higher peak than the posterior.
Could this be a visual illusion? I mean, like it definitely shouldn't be possible. We can mathematically prove that it's not, but like so can you scroll up so that we see it at the top of the screen, maybe, so that we see that orange is really higher? But
I'm getting the same with the codes
that
of
orange,
this earlier snippets.
That
it's
orange
just
is higher?
Yeah, I think it's somehow, yeah.
This is interesting. I mean, like, look, widgets are done by volunteers. We can most certainly not rule out that there's a bug somewhere in there, but like, please, I mean, like, I see what you mean here. It's kind of shocking.
I was also, I couldn't make sense out of this. I just changing
if the orange is above the green, no, you can prove that orange can never be higher than green, because like it's effectively how high it is 1 over the width of it. So, but how narrow it is, the width of it. In fact, let's briefly go over the next section, because the next section will contain the math, and then with that we will see that it can never be like that. That being said, like so the weird thing is, it doesn't seem to appear for me. Like, which values did you? Let me see if I can replicate it. Which values did you put in?
I used mu auditory is -6.
Oh, it's -6. Okay, no, that's good. Yeah, sigma
auditory is +6. Mu visual is +4, and sigma visual is +10.
It's +10. Oh. Okay. I know and understand it now. Let me explain, because this is really interesting. You remember that we use this trick that we divide by the sum of all the points that we have. The crucial thing for this to be correct is that we see all the components of it. Okay, so the trick is correct, but only if the entire Gaussian is visible. No, so if what we do is we make a mistake where we only take a piece of it, then the normalization is wrong. No, it's a very convenient trick, but if the Gaussian is so wide that it leaves the area that's visible, the normalization will be wrong, and that's where this is coming from. So let's go to the next component. The next component finally then deals with the math of that, which is we can, it's the bounds, say Sane. Yes, exactly. I was so worried that we had made a major mistake here. But what we now want to do is we want to go, and let me share my screen here. Share screen, share. Okay, so what we want to do next is we want to look at the video that is about multiplying Gaussians analytically. And then we get to do some math, which is great fun too. So everyone go back to the tutorial now.
So Gaussians are fantastic, because what we just did by pointwise multiplying the probability distribution, it turns out that we can also analytically solve that. So what do we have? We want to multiply two Gaussians, G1 and G2. We can fill in the equations for those two Gaussians. Now, I only care about how wide the results are or what the shape of the results are. I don't care about constants. So this will be proportional to this here, because see, neither of these preterms depends on x and n. So therefore we have the product of these two terms here. Now, e to the a, e to the b is e to the a plus b, which is what we use here. Now look, it's a polynomial of degree 2. So that means that we can rewrite this as a new polynomial like that. And it turns out we obtain a new Gaussian. And the new Gaussian has the property that the means of the two Gaussians are weighted inversely according to the relevant variances. This is what we have here. And we have a new standard, a new variance that is the inverse of the sum of the inverse variances. Now, for some people, this is the best way of obtaining intuition about what is going on in such Q combination cases or in such prior likelihood multiplication cases. So we prepared a little widget, which we want you to explore how the posterior depends on the means and the variances. So please play with the parameters to get an intuition. So much of neuroscience and neurotheory is built on Gaussians.
Okay, so let's just implement the analytical solution here for comparison. Now, mu integrated, what do we have? This is gonna be, let's see, it's gonna be np.sum of x times posterior. Seems right. And then mu analytical, it's gonna be here. So now what we want to do is we want to take this big equation here, mu posterior, and put it in here, mu analytic. So we have mu auditory divided by sigma auditory squared. And we'll need a bracket there. Plus mu visual over sigma visual squared. Okay. Now we need to divide that by the sum of the inverse. The sum of the inverse squared standard deviation. So therefore over 1 over sigma squared plus 1 over sigma visual squared. Sigma visual squared, that looks right. Let's run this. Oh, and of course, as always, I always forget to uncomment the various important errors. Here, the not implemented error goes away, and then I need to uncomment these lines. Visual. Let's run this. Yoo-hoo! Works. Okay, what do we have here? No, there's something wrong. I must have normalized wrong. So what we have here on the x-axis, oh no, here. No, this here we have at the bottom we have what math predicts. At the top we have what we have with our way of calculating it, with all the normalization, all the things. And look here, multiplied prior mean and analytic posterior mean exactly identical. Hooray for math, math works. Here we convinced ourselves that at least in principle, things are right. Now, here's a short little conclusion video for this tutorial. Why don't you watch the conclusion video? And then we will have like at least a little bit of time for the second tutorial. And don't get into the bonus section. We aren't doing bonus section today. So in any case, for anyone who's finished with this tutorial, let's jump right into tutorial 2. We won't have enough time to get through all of that. But I'm not really trying to teach you everything that's in the tutorial. I'm trying to get you addicted to neuromatch materials. Right, Rainier, go ahead and just ask your question.
Oh, okay. Thank you. I have a question. Is it possible to use this if, for example, the auditory and the visual are coupled equation or coupled with each other?
Ah, yes, this is very interesting. So what do we do if vision and audition are not independent? Because in practice, they often are not. And then applying the simple Bayes rule like that won't work because they're not independent. But we can still use it even if there is a dependency. It just requires us to then take into account the dependency. It's a much more complex case, and I'm pretty sure that the book explicitly deals with it. What it basically forces us to do is to then explicitly do those integrations, now where we can say basically in the base assumption that we had here is that we set the probability of vision and audition given the stimulus can be written as the probability of vision given the stimulus times the probability of audition given the stimulus. This is the so-called conditional independence assumption. That it's just there's a location and both of them are independent. If they are dependent, then we can't write it like that. We will instead have probability of X given vision and audition. And in which case we can still solve that problem, but we need to solve a different integral.
I see. Thank you.
And I apologize for misspelling Rainier's name. I think it's my autocorrect. So
it's okay. It's okay. Thank you.
Great. Let's jump right into tutorial 2 if you're ready. Let's listen to the introduction there. So tutorial 1 is about the base if we have 2 Gaussians. Tutorial 2 is what if things are no longer just simple Gaussian.
Welcome to part 2, mixture of Gaussians and causal. So in the example before, I told you how you will often feel the sound coming out of my mouth despite the fact. Now, then it turns out that that only works to a certain degree. We can try and give you an example. So we'll do now. Put all the sound on the left side. The video faces the right side. Here's your phone max. Seeing that sound comes from the left and you see one face on the right. Close to the screen, you will see a breakdown. So it doesn't sound like the sound is coming out of my mouth. So we can study that in the laboratory, just like before. So what's the difference? Well, it turns out that the only difference is that in standard experiments in that field, we look at two things that are very compatible. A visual stimulus somewhere here, sound like somewhere close by. If we make that difference very large, we get into different. And now we will build a Bayesian model for this case. Like we want a model that now also can describe the phenomenon that if we make two things very different from it, that they break apart, that they're processed independently. So we will build another Bayesian model. So we again assume that vision is near perfect and sets up a prior belief of where the auditory stimulus may occur. But we now assume that it's not the case that in all cases we expect the auditory stimulus to be close to the visual. But we assume that there's two implied cases. There's the common case, where the assumption is that the visual stimulus must be very close to the auditory. And then there's an alternative case, the independent case, where we don't believe the two of them to be very close to one another. If anything, we allow the auditory stimulus to be very far away from the other. And we again assume that audition has the constraint of the irreduced uncertainty, and we assume again that the brain has the objective of minimizing estimation noise. But what we see is like it's almost the same model. It's just we take one where we did a strong simplifying assumption that the two things always belong together. And now we relax that assumption. So what do we assume now? We assume that the vision-induced prior isn't just a Gaussian, but it contains two parts. The common cause part, which is the Gaussians we had it before, which is the belief that the auditory stimulus often should be coming from close to where the visual stimulus is. But then we assume a largely independent case where we might believe that they're somewhere close to one another, but it can be quite far away. So that's the so-called independent case. Now, how should we model this mathematically? Well, we can say we want to have a mixture of Gaussians model, where we have one Gaussian that describes what happens when they're close to one. Now, like here, the standard deviation will be small. This is this narrow standard deviation. Here, the not common case, or the independent case, where the standard deviation will be very large. We might even want to believe that it's arbitrarily large. So this is the model, no? Like it implicitly assumes that there's two, that the prior, what that is set up by vision, can have two very different cases. Either it belongs together and there's a common cause and therefore the prior is narrow, or otherwise it's wide, and both of them are possible. And you see we have a parameter here, key common, that tells us how important one of them is relative to the other. Now it's time for you to implement that. Calculate the combined prior that has both components.
Cool. So for everyone who's comfortable with that, implement it yourself. The equations are again just there. See here, mixture. We have P common times the Gaussian with mu common sigma common, and 1 minus P common with the Gaussian independent and sigma independent. I will also be implementing it at the same time. I might need help if I make a mistake here. Let's see. Gaussian independent. Okay, so now we need a Gaussian for the independent case. I'll be my Gaussian with x, comma. And now what's that mean? The mean's gonna be the same. Mean. We'll have the independent sigma here, what's it called? Sigma independent. Okay, now we need to make a mixture. P common. P times Gaussian plus, and then we'll have plus P common times and And here comes a huge surprise, which is we will need to normalize it. The mixture is mixture divided by mixture dot. It should be it's on our oh, look, here we have it. Great. And if you're roughly at the same timing with me, feel free to watch the second video of this section already.
So now that you have implemented the Mixture-of-Gaussian model, I briefly want to emphasize that this is a case of marginalization. We will hear more about that later. But the prior is the sum of the common and the not common models predictions. And by adding them together, we are effectively considering both possible values of an unknown variable. The unknown variable, is it dependent or is it independent? Is it common cause or is it independent? Now, given that we have the prior, which now is like just slightly different, like it's just the sum of two Gaussians, we can calculate the posterior using Bayesian. And this shows you the strength of the Bayesian approach. We have a completely different prior, and yet we can use exactly the same mechanisms. Like the posterior again is the prior, which now is different, times the likelihood and normalized solution. So we now want to multiply Gaussians with a mixture of Gaussians, which just like before is proportional to the prior times the likelihood. Now it's time for you to do that. Calculate the posterior in this case for the mixture of Gaussians, or in other words, causal inference model.
So I'll be playing a little bit with this now. Let's see. A new auditor. Let's change the auditor. What happens here? Look, if we're very far away from it, the vision is definitely no capture as we had it before. Oh, no, it does capture. But there's an inner region where it does capture. Outer region definitely does not capture. Very cool. Let me listen to the last video again. We'll be ending in 2 to 3 minutes here. I know not everyone's finished yet, but I want to get the chance to just say bye, tell you what this is all about, and just give you the chance to ask any last questions.
So what did we just see? There are now two different modes here. If the auditory stimulus and the visual stimulus are really quite close to one another, then we have a region where we have linear integration, where the visual stimulus has a very strong influence on the auditory stimulus. And then there's the other mode. If we are far away, it has very little influence. And then there's a relatively steep transition between these two modes. And this is what's meant with causal inference. If we have reasons to believe that they have a common cause, then there's strong influence. And if we have reasons to not believe that, that influence actually goes away. And I should just mention in that context, you can ask these models to predict a lot of different things. So in this case, for example, you can say, if we vary how much the visual and the auditory stimulus differ from one another, we can ask people to say, well, do you think that those two belong together? And it turns out that the very same model can also explain such data. So now let's talk about the experimental strategy that people usually use. What people do is they vary the disagreement between Qs. They measure how one influences the other. And then they test the hypothesis that the impact is large if they're close to one another, and small if they're far away. And again, we find this in many domains: vision and audition, price and likelihood, all kinds of cases in cognitive science. So what have we seen so far? The Bayesian framework allows us to deal with arbitrary probability distributions. Gaussians give rise to linear combinations. Mixture-of-Gaussians give rise to causal inference-like effects where we have an interaction that breaks down as soon as the difference is too large. Behavior then becomes very nonlinear. And it's a biological principle. Integration tends to be linear for small difference and tends to break down for large differences between Qs.
Okay, great. So I think we have finished for today. I want to thank everyone for participating, but I want to give you at least another 5 minutes or so where you can ask me questions. So what questions do you guys have? And of course, tomorrow I'll be talking about more research-based ideas in that same space. But I thought the tutorials are useful because it gets you to actually implement things, and it's always good to see what's really behind something. Good to see you again, Vatsala.
Yeah, it was very interesting, very interactive. So participants, you can unmute yourself and ask questions. So ask away.
Hello.
Yes, Fernando, you are audible.
Hello, I would like, thank you for your talk. I would like to ask, how does this Bayesian approach relate to the normative approach that you gave us at the beginning of the talk? What is the relation?
Yeah. Yes, great question. So it very naturally comes in many situations. So in the real world, we will usually not have all the information. If you have all the information, then the problem can usually be seen as an optimal control problem. But if we miss some information, like our eyes aren't perfect, our ears aren't perfect, nothing is perfect. Even if your eyes would be perfect, you wouldn't see what's behind something. So in the real world, we always have this level of uncertainty about the things that we don't currently observe. If you want to behave optimally in a world that you don't completely observe, the only thing you can do is kind of be probabilistic about it. Say like, well, it could be this or it could be this. And like, think about people, like you talk with someone, maybe they're a nice person who wants to help you, or maybe they are just like, they are to rob you. If you want like this level of uncertainty about the things that aren't directly observable is always there. And now Bayesian methods are just the clean ways of basically calculate. No, what is Bayesian statistics? It's just calculus with probabilities. So basically the Bayesian methods, you use them to calculate what you should ideally do in a case where there's uncertainty about the world. So in that sense, Bayesian models are a specific subset of normative models, namely those models where uncertainty matters, and namely those methods, or like the way I've been using it here, namely those methods that don't require really complicated control strategies. So you can say, maybe in chess, there's uncertainty about what someone else is trying to achieve. But the difficulty in chess isn't primarily that I can't observe what they want to achieve. The difficulty in chess is that I'm planning and you're planning and we are in that adversarial situation. So in that sense, Bayesian methods in the notion that I use here and that our book uses cover a specific subset of the overall set of normative models.
Any other questions? I think they're still digesting.
Well, Maybe some people are still coding at this time. If there's no more questions, I'll meet you tomorrow, roughly at this time of the day. And then we will get to go further into the space and see applications of these Bayesian ideas.
Sounds wonderful. Rainier has a question. Go ahead, Rainier.
Oh, thank you. I found another weird case in the code. Yeah, may I share this my screen?
Sure, please, absolutely.
Okay, I'm really not sure what is happening here, but I found something that that the likelihood can lessen my prior belief, that the peak of my prior belief with this new peak. Is that what this means?
Yes. Okay. So I think I can. You're finding a somewhat similar problem. So if you make sigma common extremely narrow, then it kind of will live between. It will like live between the bins of your grid. And therefore weird things can happen. And you're saying it goes negative here, is that it?
Yeah, I think it means that my posterior belief will be much lower, or I'm becoming more uncertain after I apply the likelihood.
Yeah, you have posterior versus again, I believe this is you found another mixture artifact. Now, so you went towards sigma common is 0.01. And if you look into the code, I bet you that the binning is about 0.01. So you're in that range where kind of basically this whole algorithmic way of dividing the x-axis into lots of equal sized chunks that works extremely well, provided that you see everything that's going on, the whole Gaussian, but also provided that you basically see the data. Now, like if you want to have enough points on the x-axis that you see what's going on. If you don't, then arbitrarily bad things happen. So the code basically doesn't support stuff that is much narrower than say 0.1 here.
Oh, okay, I see. Thank you.
Okay, wonderful. Great. You're pushing the code to its limits. And I believe it's Daniel Walpert's talk for you guys right now.
In about half an hour, we give them a break.
So you do get a break. Breaks are important. Have some coffee. Coffee's good. Great. Well, thanks so much for having me then.
Thank you so much. This was very fun. Thank you. And look forward to more on this tomorrow.
Thank you. See you tomorrow.
Bye.
Thank you.